Welcome to the deep dive.
Glad to be diving in.
Today we are opening the file on, well, a single event happened just over 2 centuries ago.
Yeah, on a remote Indonesian island.
And it just absolutely rewrote the rule book. I mean, for global climate, history.
Even art, surprisingly enough.
We are plunging into the 1815 eruption of Mount Tambora.
It's a huge one.
Now, if you've heard the name, you probably think the year without a summer.
Yeah, that's the most famous connection, definitely.
But our mission today, well, it's to go way beyond that footnote. We want to understand the how.
The mechanics of it.
Exactly. How did one geological catastrophe way out on the island of Sumbawa throw enough stuff into the air to just, fundamentally force global climate systems into chaos?
And lead to humanitarian disaster across continents.
Right. It's not just volcanology. It's this terrifying lesson in how connected everything is.
And how fragile those systems can be.
Yeah.
And when you say catastrophe, we really need to stress the scale right up front. This was the most powerful volcanic eruption in recorded human history. Full stop.
Wow.
It was classified as a VEI-7 event. That's the Volcanic Explosivity Index.
Yeah.
Measures the erupted material.
Okay, VEI-7. Now, most people today, they might know Mount St. Helens in 1980.
That was a VEI-5. Significant, but much smaller.
Or maybe Pinatubo in 91. That was huge news.
Pinatubo was a big one, a VEI-6.
So St. Helens a 5, Pinatubo 6. How much bigger are we talking when we jump to a 7 like Tambora?
Well, the index is logarithmic. So each step up isn't just adding one, it's a huge leap in power.
Okay.
A VEI-7 eruption like Tambora is a full order of magnitude, so 10 times larger than a VEI-6 like Pinatubo.
10 times Pinatubo.
In terms of ejected volume, yes. The baseline for a VEI-7 is ejecting around 100 cubic kilometers of material.
That's hard to even picture.
It is. Now, when scientists get really specific, they look at something called the dense rock equivalent, or DRE. That's the volume if you compressed all the ash and pumice back into solid rock.
Okay, the actual rock missing from the mountain.
Exactly. And for Tambora, the DRE estimates are between 37 and 45 cubic kilometers.
37 to 45 cubic kilometers of solid rock. Just gone. Blasted out.
Pretty much. It was quite simply a world-altering explosion of rock and gas.
A monster. And it didn't just sneak up on the world either. It announced itself with this terrifying global sound effect.
Ah, yes. The sound waves.
That anecdote always gets me, the confusion it caused. People literally over 1,000 miles away.
Hearing these massive continuous explosions.
And thinking it was just distant cannon fire, like preparing for battle.
It's an incredible detail. The detonation sounds were clearly heard in Makassar. That's on Sulawesi, 380 kilometers away.
Okay, that's already quite far.
But the reports go much, much farther. Batavia, which is now Jakarta, that's 12,260 kilometers away.
Wow.
Ternate, 1,400 kilometers. The energy transfer through the air was just phenomenal.
And what really just hammers home the sheer energy, those documented reports from Truman in Sumatra.
Over 2,600 kilometers away.
Yeah, and people there heard what they thought were guns firing. Sir Stamford Raffles.
He documented so much of the aftermath, right? He was lieutenant governor of Java then.
He was a key source for us.
He noted in his memoir that almost everyone thought it was a naval battle or some kind of military engagement.
Raffles' observation really captures that initial misunderstanding perfectly. It was so convincing that a detachment of troops actually marched out of Jakarta because they thought a nearby post or maybe a ship was under attack.
They mistook this massive geological event for human warfare.
Completely.
And some recent analysis even suggests the rumbles might have been audible even further, like over 3,350 kilometers away. Nong Khai, Vientiane. Though those are less certain.
Still, it's possible. It just establishes the sheer magnitude. It was probably the largest sonic event of the entire 19th century.
What a way to set the stage for a disaster. A sound so vast to trick people across thousands of kilometers.
It really does. So, okay, let's look at the timeline now. What actually happened to the mountain? Okay, let's unpack this. Tambora, before 1815. It was this huge, cone-shaped stratovolcano. Looked magnificent, apparently, but dormant for centuries.
Right, and dormancy in these big volcanoes isn't exactly peaceful. It often means the magma chamber underneath is cooling, crystallizing.
And building pressure.
Precisely. As magma cools and solidifies, gases get released to get trapped, and the pressure just builds and builds relentlessly.
We're talking serious pressure here.
Extreme pressure. Estimates suggest something like 4,000 to 5,000 bars of overpressurization inside that magma chamber.
Wow.
The mountain was essentially a ticking time bomb, holding centuries of pent-up energy.
And the science started well before the big one, didn't they? Sources say 1812, it began rumbling.
Yeah, 1812. Rumblings. A small dark cloud seen near the summit. That was the first sign the structure was maybe starting to fail. The beginning of the end, you could say.
The first really big bang, though, the one that caused all that cannon fire confusion, that was April 5th, 1815.
That's right, April 5th. A massive eruption, huge pressure release, generated those thunderous sounds heard hundreds of miles away. But even that was just the warm-up act.
The main event, the one that put Tambora in the history books forever, that was April 10th. In the evening, yes, April 10th, around 7:00 p.m. local time, the eruptions just went into overdrive. Eyewitness accounts describe 3 distinct plumes of fire rising up. 3.
Yeah, and then merging into one single colossal column. Descriptions say the entire mountain seemed to turn into a flowing mass of liquid fire.
Liquid fire. Just a horrifying image. Magma, gas, superheated rock all flowing. The physical violence was just staggering. Then around 8 p.m., the sky itself started falling.
What do you mean?
Pumice stones. Rocks, often up to 20 centimeters in diameter, that's like softball size, started raining down on the surrounding area.
Whoa. Followed by heavy ashfall between 9:00 and 10:00 p.m. Imagine being there. Total darkness, deafening noise, and then massive rocks falling out of the sky.
Terrifying. And the energy was so immense it created its own localized weather.
Like a storm. More like a whirlwind. A violent whirlwind generated by the eruption blast itself apparently ripped through the village of Sagar, which is now Sangar.
What did it do?
Blew down nearly every house. Carried debris, even large trees, high up into the air. Just incredible power.
And the geological impact. The energy release numbers are just mind-boggling.
They really are. The estimate is equivalent to about 33 gigatons of TNT.
33 gigatons.
An almost incomprehensible force. And remember, before this, Tambora was one of the tallest peaks in the entire archipelago, around 4,300 meters high.
After April 10th.
Afterwards, the peak height was slashed by about a third, down to only 2,851 meters.
It just blew the top third of the mountain clean off.
Yeah, essentially, yes.
Yes.
The summit was obliterated, replaced by this massive hole, a caldera.
How big?
6 to 7 kilometers across, and about 600 to 700 meters deep. That caldera is the scar. It's the physical proof of where those 100 cubic kilometers or so of mountain used to be before it got turned into ash and blasted skywards.
A direct measure of that colossal volume we talked about. Hashtag tagged 1.2 local tsunami and pyroclastic flows. Of course, the destruction wasn't just falling rocks. There were these immediate secondary effects, just as deadly, moving sideways across the land and sea.
Absolutely. We have to talk about the pyroclastic flows.
These are the super hot, fast-moving currents of gas and rock.
Exactly. Scorching hot, moving incredibly fast down the slopes. They cascaded down every side of the peninsula where Tambora sits.
Wiping out everything.
Everything in their path, including the main village of Tambora itself. These flows meant total annihilation over an area of about 874 square kilometers right around the mountain.
And all that material, rock, ash, gas, rushing into the sea must have done something.
It did. It displaced a huge amount of water, generating a tsunami. Not a giant Pacific-wide one, but definitely moderate-sized and absolutely devastating locally.
When did that hit? Pretty quickly. Around 10:00 p.m. that same night, April 10th. In Sangar, the waves reached up to 4 meters high. 4 meters is significant.
It is. We also have records of smaller waves, maybe 1 to 2 meters, hitting Basuki over in East Java. And similar 2-meter waves reported way out in the Molucca Islands.
So it spread quite a bit, and the death toll from the tsunami alone.
The immediate tsunami deaths are estimated around 4,600 people, just swallowed by the sea right after the eruption climaxed. Hashtag tag 1.3, the aftermath on Sumbawa and Lombok.
The blast, the flows, the tsunami, horrifyingly fast, but then the slower tragedy unfolds on the nearby islands, Sumbawa and Lombok. The ecosystem just collapses.
Complete collapse.
Yeah.
Leading to famine and disease. The eyewitness accounts from the weeks after are just gut-wrenching.
You mentioned Alteep Phillips earlier, sent by Raffles to survey.
Yes. His report is shocking. He described finding the remains of several corpses just lying along the roadsides weeks later.
Oh, God.
Villages were almost entirely deserted, he wrote. Houses fallen down. Why? Because the survivors had dispersed in search of food.
Just scattered, trying to survive.
The environmental destruction was total. All vegetation on Sumbawa was wiped out. Gone.
And the debris wasn't just ash, right? There were these huge rafts.
Yes. Uprooted trees, all mixed up with pumice ash, washed into the sea. And they formed these immense floating rafts, some reportedly up to 5 kilometers across.
5 kilometers? That's enormous.
Huge. They were a real hazard for ships. British ships, like the Fairlie and the James Sibbald, ran into these massive pumice rafts months later, as far as 3,600 kilometers west of Tambora.
Just floating evidence of the eruption's power months later and thousands of kilometers away.
A floating monument, exactly.
Now the death toll. It's grim, but it seems complicated. The numbers vary so much in historical accounts.
They do. And that variation really speaks to the chaos of the time and just how hard it was to count victims accurately in the early 19th century, especially in a disaster zone.
It's important to separate the causes, right? Direct deaths versus indirect.
That's critical for historians. Direct fatalities, the people killed instantly by the blast, the pyroclastic flows, the initial tsunamis, that number is generally agreed to be around 10,000 to 11,000 people.
Okay, 10 to 11,000 direct deaths. But the indirect numbers, that's where it gets murky.
That's where the real controversy, or at least wide variation, comes in. Early estimates, like from a Swiss botanist named Zollinger, who visited Sumbawa later, he suggested maybe 28,000 indirect deaths from starvation and disease just on Sumbawa and Lombok.
Okay.
But then, much later, in 1949, you get this figure from a Russian scholar, Petrushevsky. He estimated an astonishing 88,000 total deaths.
88,000? That's a huge jump. How did he break that down?
He estimated 48,000 on Sumbawa and 44,000 on Lombok. So a massive number attributed to indirect causes.
So why such a huge difference? Was it just bad record keeping back then, or something else?
Seems to be a mix. Raffles himself, even though he tried to be meticulous, admitted struggling to get accurate numbers. Local governance just completely broke down.
Understandable.
Later researchers, particularly Tanguy and others in 1998, went back and really scrutinized Petrushevsky's high numbers. They concluded they were likely unfounded. Probably issues with how he extrapolated data, maybe definitions of death due to eruption.
So what's the current consensus, the number most historians accept now?
Based on reevaluating Raffles' notes, Zollinger's work, and later scientific reconstruction, the widely accepted estimate lands at about 11,000 direct deaths.
Okay.
And around 49,000 indirect deaths from the famine and disease that followed.
49,000 indirect. So bringing the total regional loss of life to
at least 71,000 people. A devastating demographic blow to that region.
71,000. Just incredible. And the specific cause of death for many who survived the initial blast? It was particularly awful.
Yes. Leighton Phillips recorded this widespread, severe, violent diarrhea in the worst-hit areas.
And they knew what caused it.
The local people attributed it, and Phillips agreed, to drinking water which has been impregnated with ashes.
The ash poisoned the water supply.
Exactly. Compounding the starvation with disease. Just layers of disaster.
So the immediate local story is just immense violence, total ecological collapse, starvation, disease. Horrifying.
Absolutely.
But as devastating as that local picture is, it almost pales in comparison to what Tambora did next, exporting its effects to the entire planet.
That's where the story goes global, and arguably even more terrifying.
Right. The sheer violence of the initial blast is one thing, but that regional death toll, awful as it is, was eventually dwarfed by the global tragedy. Let's talk how. How does an explosion in Indonesia cause snow in New York the following June? What's the physics? Hashtag 2.1, the atmospheric mechanism. This is really the core of the deep dive, understanding this mechanism, and it boils down to two main things. How high the eruption went and what it put up there, the chemistry. Okay, how high did it go?
The Tambora eruption column was unbelievably powerful. It punched right through the normal weather layers and reached far, far higher, over 43 kilometers high.
43 kilometers? Why is that altitude so critical?
Because it gets you well into the stratosphere. See, our weather, rain, clouds, wind systems, that mostly happens down here in the troposphere.
Okay.
If volcanic ash or gas only reaches the troposphere, it gets washed out pretty quickly by rain, mixed down within days or weeks usually.
Right.
But the stratosphere, which starts around, say, 10 to 17 kilometers up, depending on where you are, it's different. It has what scientists call a temperature inversion. Meaning, as you go higher up in the stratosphere, the temperature actually gets warmer, mostly because ozone up there absorbs solar radiation. This temperature profile creates stability. There's much less vertical mixing between the troposphere and stratosphere. There's sort of an atmospheric lid at the boundary, the tropopause.
But if an eruption is strong enough to blast material through that lid,
then that material can stay suspended up there for a very long time, years even. It's above the weather, essentially. It won't get rained out.
And the key stuff that Tambora blasted through that lid wasn't the heavy ash, right? That fell out relatively quickly.
Correct. The heavier ash particles settled out faster, though they caused immediate local problems. The real climate culprit was something much lighter. A gas. Sulfur dioxide, SO2. Sulfur dioxide.
Tambora ejected a truly staggering amount of SO2. The estimates vary a bit depending on how you measure it, but they range from maybe 10 million tons on the very low end up to possibly 120 million tons.
Whoa, that's a huge range, but even the low end sounds massive.
It's enormous. And once that SO2 gets into the stratosphere, it undergoes chemical reactions with water vapor up there.
And forms.
Tiny microscopic droplets of sulfuric acid, H2SO4. These droplets are called sulfate aerosols.
Aerosols.
And they form this vast, persistent global layer, a stratospheric sulfate aerosol veil.
So these tiny droplets floating way up high, 10, 20, 30 kilometers up,
yeah,
they basically act like a giant mirror.
That's exactly right. They significantly increase the Earth's albedo, its reflectivity.
Reflecting sunlight back into space. Incoming shortwave solar radiation, yes. It gets reflected back before it can reach the surface and warm the planet.
And that leads directly to cooling.
Sudden, short-term global cooling, what we call a volcanic winter. Tambora was the largest natural climate-forcing event of the last couple of centuries, easily.
And the numbers show it. Global average temperatures dropped by how much?
About 0.53 degrees Celsius. That's nearly a full degree Fahrenheit, 0.95 degrees Safa, averaged across the globe in the year following the eruption.
That might not sound like a huge number, half a degree Celsius, but averaged globally, that's a massive shock to the system, isn't it?
It's a huge shock. Climate systems operate on relatively fine margins. A sudden drop like that throws weather patterns completely out of whack.
It's fascinating, too, that this whole mechanism, sulfur aerosols in the stratosphere causing cooling, wasn't really scientifically understood until much later.
Not until the Krakatoa eruption in 1883.
Yeah.
That eruption wasn't as big as Tambora, but it happened in the age of telegraphs and global science.
And it caused those weird, colorful sunsets everyone saw.
Exactly. The brilliant sunsets from Krakatoa got scientists really investigating the atmospheric effects. But Tambora had already demonstrated the principle, extremely powerfully, 68 years earlier. Proof written in, well, global famine, as you said. Pretty much. The sheer scale of Tambora's sulfur injection was key. It was just so much more than anything else in recent memory, like Pinatubo even.
And that veil spread quickly around the globe.
Very quickly.
Yeah.
Stratospheric winds distributed those aerosols fairly evenly around the globe within weeks to months, especially blanketing the northern hemisphere. Hashtag 2.2 visual phenomena around the world.
Beyond just the cooling, this global aerosol veil created some really strange and frankly unnerving visual effects thousands of miles away, things people saw in the sky.
Yes, absolutely. In the northeastern United States, particularly in 1815 and into 1816, people reported this persistent dry fog.
Dry fog, what was that like?
Well, the descriptions are eerie. It was thick enough to significantly dim the sunlight, often giving it a reddish tint. But the strangest thing, it couldn't be dispersed by wind or rain. It just hung there. Because
it wasn't really fog down low, was it? It was the stratospheric stuff mixing down.
Exactly. It wasn't tropospheric water vapor fog. It was the optical effect of that high-altitude aerosol layer.
And the sunlight was dimmed so much, people could actually see sunspots with the naked eye.
Contemporaneous accounts confirm that, yes. Which must have been truly terrifying for people who relied on the sun and sky for everything, for agriculture, for signs.
Yeah, imagine the sky just looking wrong, persistently hazy and red for months on end. That must have caused incredible anxiety.
Undoubtedly. A huge psychological impact.
But there was also this surprisingly beautiful side effect, wasn't there? Especially seen in Europe.
Yes, the sunsets and twilights. Those fine aerosol particles scatter sunlight in very specific ways.
How so?
They tend to scatter the shorter wavelengths, blues and greens, more effectively, allowing the longer wavelengths, the reds, oranges, pinks, to dominate the view, especially when the sun is low.
So you get these incredibly vibrant, colorful sunsets.
Prolonged and brilliantly colored, yes. Often described as fiery orange or red near the horizon, shifting dramatically to purples and pinks higher up. These were seen frequently in places like London, especially between June and October of 1815.
And this wasn't just a curiosity, it actually had a cultural impact on art.
It seems very likely. Sources strongly connect these unusual dramatic skies to the paintings of the great romantic landscape artist, J.M.W. Turner.
Turner's famous fiery skies.
Exactly. It suggested that the volcanic dust, those aerosols, directly influenced his palate, leading to some of his most famous works where the skies blaze with these intense, almost unnatural oranges and reds.
That's incredible. The violence of an eruption in Indonesia, filtered through atmospheric physics, ends up inspiring a major artistic movement in London.
It just shows the unexpected reach of an event like this. It wasn't just about weather and crops. It touched culture, too. Hashtag 2.3, the climate shift and the Dalton minimum.
Okay, let's look at the hard climate data again. That 0.53 degree global cooling, it wasn't just a blip. The 1810s became the coldest decade on record for the Northern Hemisphere, right?
Yes, culminating in 1816 itself, which ranks as the second coldest year in the Northern Hemisphere going back to about 1400 AD, a truly anomalous period.
And critically, as you mentioned, Tambora didn't happen in isolation. The timing was, in a way, terrible. It hit when the climate was already kind of vulnerable.
Exactly. It occurred smack bang in the middle of the Dalton minimum.
Right. Can you just briefly explain what the Dalton minimum was?
Sure. The Dalton minimum was a period roughly from 1790 to 1830 characterized by unusually low solar activity. Fewer sunspots, less solar radiation reaching Earth. It's a natural cycle in the sun's output.
So the sun was already putting out a bit less energy.
Correct. This natural solar cycle likely caused some pre-existing global cooling on its own. Scientists estimate maybe around 0.2 degrees Celsius cooling attributable just to the solar minimum during that period.
Okay, so here's the crucial question then. How sure are we that Tambora was the main driver of the extreme cold in 1816 and not just, the final straw on top of this existing solar cooling?
That's a really important distinction to make. The Dalton minimum provided a cooler background state. Think of it as lowering the baseline temperature gradually over decades.
Okay.
But Tambora provided the sudden, sharp shock. The volcanic aerosol cooling is abrupt, it's strong, and its biggest impact lasts for maybe 2 to 3 years right after the eruption.
So the rate of cooling is key.
Absolutely. That sudden drop of over half a degree Celsius globally right after 1815 simply cannot be explained by the slow, gradual effect of the solar minimum alone. Tambora delivered the massive, rapid forcing that destabilized weather patterns worldwide almost overnight.
And that shock, that destabilization, it didn't just last for one bad summer.
No, the impacts lingered. The surface temperature anomalies, especially for summer temperatures in the Northern Hemisphere, remained significantly below average for 1816, 1817, and 1818. It marked a profound, multi-year disruption that just crippled agriculture. Which brings us directly to the most famous consequence. The year without a summer, 1816? That's right. The immediate result of that stratospheric aerosol veil was this complete breakdown of normal weather patterns across the Northern Hemisphere, and the human suffering it caused was just monumental, stretching across continents.
Let's start in North America, New England, Atlantic Canada. The climate shock there seems to have been incredibly direct and devastating, especially for farmers. Hashtag 3.1 North American hardship.
It essentially annihilated the growing season in many areas.
We're talking serious cold, persisting deep into the months that should have been warm.
Extreme cold, long past the usual last frost dates. In early June of 1816, there were damaging frosts reported in the higher elevations of New Hampshire, Maine, Vermont, northern New York.
Killing off crops that had just been planted?
Completely wiped out the first plantings. And then it got even worse, much worse than just a cold night.
Snow.
On June 6th, snow actually fell in places like Albany, New York, and Dennisville, Maine.
Snow in June. It's hard to fathom.
And if you were up in Cabot, Vermont, on June 8th, historical records say the snow on the ground was still 46 centimeters deep.
18 inches in June.
18 inches of snow, and crops should have been well underway. Canada got hit hard, too. Near Quebec City, 30 centimeters, about a foot of snow accumulated between June 6th and 10th.
So for farmers, say, in Massachusetts or New Hampshire, the summer was just impossibly short.
Brutally short and cold. The effective growing season in some areas was slashed to less than 80 days. Widespread harvest failures, catastrophic failures. Most agricultural crops were simply ruined. People had to resort to eating things they normally wouldn't, wild roots, pigeons, apparently even boiled nettles.
And the impact wasn't just that one bad harvest, was it? It had knock-on effects.
Absolutely. The feed shortages were severe. During the following winter, 1816 into 17, huge numbers of livestock died in New England because farmers simply had no fodder for them.
And the winter itself was extreme, too.
Temperatures in parts of central and northern New York reportedly dropped below minus 34 degrees Celsius. That's minus 30 Fahrenheit. cold enough to freeze lakes and rivers solid, cutting off transport routes they normally relied on.
The whole food system was just crippled.
Crippled by this relentless, unnatural cold. It triggered a significant migration wave. Many New England farm families just gave up, abandoned their failed farms and headed west, hoping for better land and warmer climates.
A demographic shift literally caused by a volcano half a world away. It really was. But while North America dealt with cold and migration, Europe faced something even worse: widespread famine and social upheaval. It really was. But while North America dealt with cold and migration, Europe faced something even worse. Hashtag 3.2 European famine and social unrest.
Yeah, the situation in Europe sounds equally dire, maybe even more so. Europe was already fragile, right? Just coming out of the Napoleonic Wars.
Yes, many regions were already dealing with poverty, disruption, food insecurity. The climate shock of 1816 hit this vulnerable population and pushed the continent into what's often called the worst famine of the 19th century.
What were the specific weather effects in Europe? Was it just cold?
It was a combination. Cool temperatures, yes, but also unusually heavy rains across much of the continent. Some areas saw up to 80% more rainfall than normal during the summer.
Which is terrible for crops.
Disastrous, especially for the vital grain crops. Widespread failures across the British Isles, France, Germany, Switzerland, Central Europe.
And the human cost was immediate. Immediate and brutal. Food prices shot up, doubled, tripled in some places almost overnight. This instantly pushed the urban poor, who relied on buying food daily, into starvation.
Leading to unrest.
Profound social unrest. Desperate people took desperate measures. We see widespread food riots, the famous bread riots breaking out.
Where people attacked bakeries, grain markets.
Exactly. Demonstrations turned violent. There was arson, looting, attacks on mills where grain was stored, attacks on convoys trying to transport food. This happened in many European cities across Germany, Italy, France.
And how did governments respond? Could they cope?
Caution? They couldn't, or didn't effectively. Responses were slow, insufficient. Some authorities were accused of hoarding grain or were simply overwhelmed by the scale of the crisis hitting multiple countries simultaneously. It was hard to mobilize supplies fast enough.
The displacement sounds heartbreaking, too. You mentioned Wales.
Yes, reports describe families in Wales, their harvest totally failed, having to travel long distances as refugees, literally begging for food to survive.
And Ireland. It was hit hard, too.
Famine was particularly severe in parts of Ireland. The failure of the wheat, oat, and potato harvests there was devastating. A grim foreshadowing of the even greater famine later in the century.
And the weird weather just kept coming. Ice dams in Switzerland in the summer.
Yeah, the combination of high precipitation and cold meant that some meltwater rivers froze up again. Sources specifically mention an ice dam forming in the Swiss Alps during the summers of both 1816 and 1817.
Which is how 1816 really earned that name, Year Without a Summer.
Literally. Although it's worth noting the variability. While Western and Central Europe froze and flooded, Russia, interestingly, seems to have experienced unusually warm and dry summers around this time, starting in 1850 and continuing, which shows the climate forcing didn't just cause uniform cooling everywhere, it caused massive shifts and disruptions in regional weather patterns, extremes of different kinds. Hashtag 3.3 Asia disruption and disease.
It's so important we connect this globally. The crisis wasn't confined to Europe and North America. We need to bring Asia into the picture. It suffered different but equally devastating consequences.
Crucially, yes. The cooling effect, particularly in the northern hemisphere, had major knock-on effects on tropical weather systems, especially the vital monsoon systems.
The Indian monsoons, so critical for agriculture there.
Absolutely critical. The volcanic forcing seems to have significantly disrupted the timing and intensity of the Indian monsoons,
leading to
directly to 3 consecutive failed harvests and widespread famine, particularly severe in the Bengal region of India. Agriculture there was and is completely reliant on the predictability of those seasonal rains. That predictability just vanished.
And this environmental chaos, the famine conditions, it didn't just cause starvation, it also set the stage for a massive health crisis.
Yes, this is one of the most chilling and far-reaching consequences. The climate disruption in India is directly linked to the emergence and subsequent global spread of a new, particularly virulent strain of cholera.
Cholera, originating in Bengal in 1816.
That's the link scientists and historians make. The conditions created by the climate change, the failed rains followed by flooding, the changes in water levels and temperature, the famine weakening the population created ideal conditions for the cholera bacterium, Vibrio cholerae, to mutate or thrive and spread rapidly through contaminated water sources across Bengal. So, a direct line. Volcano, climate change, famine, epidemic, disease. It appears so. A truly terrifying cascade effect.
And the disruption didn't stop in India, did it? China was affected too.
Yes, the alterations to the monsoon patterns also caused severe flooding along the Yangtze River Valley in China.
Forcing people to flee.
Thousands were forced to abandon their homes and ruined farms in coastal and riverside areas due to the floods. More displacement, more misery.
And the health problems echoed back towards Europe as well. Typhus.
Yes, the general climate anomaly across Eurasia. The widespread cold, damp conditions, the mass movements of starving, weakened people is blamed for worsening and spreading typhus epidemics. These ravaged parts of southeastern Europe and the eastern Mediterranean between 1816 and 1819 is just layer upon layer. One explosion triggers this domino effect. Climate chaos, crop failure, starvation, forced migration, and major disease outbreaks across 3 continents. The scale of the indirect devastation is truly staggering. It's hard to think of another single, localized natural event in recorded history that had such a broad, simultaneous, and long-lasting negative impacts on human societies across the globe.
It really stands as the definitive historical example, doesn't it? How geology can drive global socioeconomic and public health crises.
Absolutely. A stark lesson from the past. Hashtag check outro.
So our deep dive today, it's taken us on this incredible, if grim, journey. Started with a 4,300-meter volcano in Indonesia.
And ended with snow in June in New York.
Bread riots in Europe.
And the emergence of a global cholera pandemic in India.
We have to come back to those numbers. That estimated 71,000 regional deaths near Tambora itself.
And then the estimated 90,000 additional global deaths, mostly linked to the cold, the famine, the disease.
All an indirect consequence of that single tropical eruption thousands of miles away.
That figure alone just speaks volumes about how vulnerable global systems were, even then, to sudden climate shocks. But what also makes Tambora stand out is just how long the impact lasted.
Right. It wasn't just one bad year.
No. The really weird atmospheric conditions, the direct effects of the aerosols, persisted for the better part of 2.5 years, causing havoc in multiple consecutive growing seasons.
And the actual cooling effect on the climate system lingered even longer than that initial aerosol veil, didn't it?
It did. The way the stratosphere absorbed heat and then slowly rebalanced led to a delayed surface cooling effect that actually persisted for about 9 years, right up until around 1824.
9 years of subtle but significant impact. The 1810s really were a volcanically disturbed decade. They absolutely were. And we know this with incredible certainty now, thanks to science that wasn't available back then. Ice cores. Drilled from Greenland and Antarctica. What do they show?
They provide a frozen atmospheric record. Scientists can analyze the layers of ice for trapped volcanic aerosols, particularly sulfates.
And Tambora left a clear signature.
The clearest, most dramatic signature in the record. The data is unambiguous. The Tambora eruption caused the largest spike in sulfate concentrations found in ice cores going back at least 5,000 years.
5,000 years. Bigger than anything else in that huge time frame.
By far. You see this massive spike in sulfate appearing in the ice layers corresponding to early 1816, and then it gradually tails off over the next few years. The amount of sulfur ejected is estimated from this data to be around 25 to 30 teragrams.
How does that compare to, say, Pinatubo again?
It's roughly 10 to 15 times the amount of sulfur ejected by Pinatubo in 1991. Just a different league entirely.
It's such a powerful, chilling reminder that our climate system can be dramatically forced into chaos by natural events.
Especially when, as was the case back then with the Dalton minimum, the system might already have existing vulnerabilities.
Yeah, that's a key point. Tambora didn't create those famines out of thin air. It massively accelerated and exacerbated problems that were already there. Regional poverty, the stresses from the recent wars, maybe existing localized droughts.
It pushed vulnerable systems over the edge. Which brings us, I think, to the final, really provocative thought to leave our listeners with.
Okay. Think about it. Back in the early 19th century, a time when food systems were mostly local, global population was much smaller, and the planet was actually in a natural cool phase. Even then, this single eruption caused the worst famine of the century, killed tens, maybe hundreds of thousands, indirectly worldwide.
So, now consider today. What if a VEI-7 eruption, a Tambora-scale event, were to happen now? In our current world, with ongoing anthropogenic global warming, with our incredibly complex and interconnected global supply chains, our reliance on monoculture farming, billions more people.
What level of disruption or even collapse could that sudden, forced climate shift trigger in our modern society?
It's a sobering question. The Tamboras story really underscores this profound vulnerability. It shows that even in our hyper-connected, technologically advanced world, a massive geological event on one remote island could still potentially bring the entire planet to its knees.
A lesson from 1815 that feels incredibly relevant today. Thank you for joining us for this deep dive.